When people talk about C++ versus Rust, they're not really just comparing two programming languages. What we're actually looking at is a fundamental clash of philosophies, a really deep divide over the right way to build the most critical software in the world. So let's break down what this schism is all about.
And look, that might sound a little dramatic, but it's really not an exaggeration. The outcome of this debate, this showdown, is going to define the security, the reliability, and the performance of, well, pretty much everything. From our operating systems to the cloud infrastructure that runs the internet, the stakes here are incredibly high. All right, so first up, we have to talk about the reigning champ, C++. For almost 40 years, it has been the undisputed king, the language that built our digital world. And it was all built on one single powerful idea: give the developer absolute total control over the machine. Now, the thing about C++ is that it's not some dusty old relic. It's a living, breathing language that's constantly evolving. That jump to what we call modern C++ back in 2011 was absolutely huge. It brought in new features to help manage things more safely. But its core DNA, that foundation of ultimate control, that's never changed. This right here, this is the secret sauce. The zero overhead principle is the core promise of C++, and it's what made it so dominant. It basically says the language will never get in your way. You will not pay a performance penalty for something you didn't explicitly ask for. This is precisely why it's the go-to language for things like high-frequency trading and blockbuster video games, where every nanosecond counts.
But here is the catch, and it is a huge one. With all that unleashed power comes unchecked responsibility. The C++ compiler trusts you, the developer, completely, which means it also trusts you to make absolutely catastrophic mistakes. I'm talking about things like buffer overflows. That's where your program tries to put too much data in a box and it spills out, corrupting everything around it. Or even worse, data races, where two parts of your program try to mess with the same piece of memory at the exact same time, leading to total chaos. These aren't just small bugs, they are the root cause of so many of today's security vulnerabilities.
And that safety crisis, all those bugs, basically left the door wide open for a new challenger. Rust showed up on the scene with a radical, almost revolutionary question. What if speed and safety weren't a trade-off? What if you could have both, guaranteed? If you want to know why Rust had to exist, just look at this number. Get this. Around 70% of the most severe security bugs that companies like Microsoft and Google deal with are caused by these exact kinds of memory safety errors. The very bugs C++'s philosophy allows. Rust was designed from the ground up to make an entire class of these bugs literally impossible to write. So how in the world does it pull this off? Well, it all comes down to a system people call the safety contract. Think of it as 3 simple rules that the compiler enforces with an iron fist. First, ownership. Every single piece of data in your program has one and only one clear owner. No confusion. Second, borrowing. You can lend that data out, but there are strict rules. Either one person can borrow it to change it, or many people can borrow it to read it, but you can never, ever do both at the same time. And third, lifetimes. The compiler checks to make sure nobody holds on to borrowed data for longer than the original data actually exists. It sounds complex, but these 3 rules working together mathematically eliminate memory bugs in safe code. It's a game changer. And this totally flips your relationship with the compiler on its head. In the Rust world, the compiler isn't just turning your code into an executable. It's more like a strict but fair mentor. Some people call it a benevolent dictator. It forces you to prove your code is safe before it will even compile. So yeah, you end up fighting the compiler sometimes, but you're not fighting those awful, mysterious bugs at 2 a.m. And look, the appeal isn't just about safety, not by a long shot. Rust was built with a modern developer in mind. It has this incredible unified build system called Cargo that just works. The syntax is modern and expressive. It makes concurrent programming, which is usually terrifying, way less scary. And the whole ecosystem of libraries is built with safety in mind from the start. Okay, so this is where it all comes together. This is the core of the conflict, the real philosophical showdown. Is it better to have the ultimate control that C++ offers, or the unwavering guarantees that Rust provides? At the end of the day, it all boils down to one simple question. Who or what do you trust? C++ puts its faith entirely in the developer. It assumes you're a genius who will never make a mistake, and it prioritizes your freedom above all else. Rust, on the other hand, puts its faith in the compiler's mathematical proofs. It assumes that all humans, even the brilliant ones, are fallible and need a safety net.
And nowhere is this difference clearer than when you talk about concurrency, getting your code to do multiple things at once. In C++, this is notoriously dangerous. One tiny mistake can lead to one of those data races we talked about. But in Rust, the compiler actually verifies your concurrent code. If your program compiles, you get a mathematical guarantee that it is free from data races. This is what the community calls fearless concurrency.
So, if we lay it all out side by side, you can really see the philosophies in action. With C++, memory safety is manual. You have to opt into safer patterns. Its build system can be fragmented, but its interoperability with C is second to none. With Rust, safety is the default. It's enforced. The build system, Cargo, is totally unified. And while its performance ceiling is incredibly high, it's generally seen as comparable to well-written C++. The choice really depends on what you value most.
All right, enough theory. Let's talk about the real world. Where are these philosophies actually winning battles out in the industry right now? Make no mistake, C++ is still an absolute titan in some massive domains. The entire AAA gaming industry is basically built on C++ with engines like Unreal. In high-frequency trading, where you need to squeeze out every last nanosecond of performance, its raw power is non-negotiable. And then you have aerospace and automotive, where there are decades of certified, battle-tested C++ code. It's not going anywhere anytime soon in those fields. But on the other side of the coin, Rust is making huge waves in all the new foundational software. It's quickly becoming the language of choice for anything where security is paramount. Cloud providers like AWS and Microsoft are rebuilding critical parts of their infrastructure in Rust. It's now the second official language for the Linux kernel, and it's totally dominating the world of WebAssembly, bringing high-performance code to our browsers safely. That means a more secure, less crash-prone web for all of us. So where does all this leave us? Well, it's clear that this debate is bigger than just C++ versus Rust now. It signals a fundamental shift in what we expect from our most important software. We are entering an era of guarantees. Because, let's be real, you can't just flip a switch and rewrite the entire planet's C++ code. It's just not feasible. And that's why we're seeing this fascinating new category of languages pop up, the so-called successors. Their big goal is to give you the best of both worlds, Rust-like safety, but with perfect, seamless compatibility with the billions of lines of C++ that already run our world. And they're all tackling the problem from slightly different angles. You've got Google's Carbon, which is all about letting you migrate a C++ project piece by piece. Then there's CPP Front, which is trying to evolve C++ from the inside out by adding a safer syntax on top. And you have other languages like Vau that are exploring brand new ways to think about safety models. And this brings us to what is maybe the most important takeaway of all. The real winner of this showdown, it isn't going to be a single language. It's a principle. What Rust has successfully done is prove to the entire industry that safety and performance are not opposites. You don't have to trade one for the other. It has forced everyone to take memory safety seriously, and that has shifted our expectations for building foundational software forever. So, I'll leave you with this question to think about. As we build the next generation of software, the code that will run our lives, what do we value more? The absolute freedom and ultimate control that one philosophy offers? Or the provable correctness and mathematical guarantees offered by another? The choice we all make as an industry will define the digital world we're all going to live in.